Okay, good afternoon. I'm Alex Vlachos from Valve. This is the Advanced VR Rendering talk. So here's what I'm going to cover today. I'm going to start by giving a brief overview of what we've been doing at Valve with VR. There's been a few press announcements recently. I'll mention them briefly. I'll start with giving a pretty brief overview of stereo rendering and different methods for doing that. I'm not going to spend too much time there. It's a pretty well-known topic, but I do want to cover a few things. Then I'm going to get into the meat of the talk. The next three sections are really the bulk of what I want to talk about today. The first section is going to be on timing. It's not performance, but timing, meaning how we schedule work, why prediction matters, how you schedule for that, where vsync comes into play, and how we get rid of a bunch of GPU bubbles that you might get if you do some of the more obvious things. The next section is going to be all about aliasing. Okay, we're going to cover specular aliasing, geometric aliasing, and a bunch of solutions where we get anisotropic lighting that kind of falls out of the solution to solving a bunch of aliasing problems. And the last section is going to be a bunch of miscellaneous VR rendering topics that are all about 1 or 2 slides each, but super interesting, super valuable. I hope that's interesting. And they're aimed at either buying you a bunch of perf or performance. So let's get into it, okay? One thing to note is in the top right corner is slide numbers. If you have a question at the end, remember the slide number from your question so I can jump to it quickly. This is it's going to be a pretty dense talk. The talk I really want to give today is about a 2-hour talk, but I don't have 2 hours, I've got 1 hour. So I've cherry-picked the topics I want to talk about, but I'm going to get kind of deep in some of them and go kind of maybe a little fast, hopefully not too fast. Okay, so what have we been doing at Valve? So we've been doing VR research for over 3 years now, and we have a full team of hardware, software engineers. We have optics experts. We've got everyone you need in our pipeline to actually make an HMD, to design it from the ground up. So I've had sort of the luxury of being able to just sit down with an optics expert and ask them questions about how the lenses work, how optics work, and you know, hardware experts that understand everything about the panels more than I will ever understand about panels. So I've sort of been at an advantage where I've been able to ask every question I want to a hardware team that has made HMDs. This is on the right here are 3 generations of our HMDs in different tracking systems. Some of these port track controllers. The team at Valve came up with a bunch of interesting things where they figured out low persistence displays, why that matters, and global displays where the entire display is lit at the same time instead of a rolling display. And we've also created the SteamVR API, which is a cross-platform API. And there's also a form of it that doesn't require Steam, which is called OpenVR. And we're not going to talk too much about that today. This is not a sponsored session, so I'm not here to pitch that API. But I will make mention of it where it does matter, where certain problems that I'm presenting, you can get data through that API. Okay, so I had to pick an HMD to give the talk based on, so this was the best target for me. I know this HMD the best. If you're unfamiliar, if you haven't been following the industry news, we announced a partnership with HTC in the last few days where HTC is going to be making an HMD called the HTC Vive. The developer edition, they say, is going to ship in the spring, and they're going to ship a consumer version by the end of the year. So let's talk about the specs of the developer edition, and the talk's going to be based on the specs of this HMD. So it's a refresh rate of 90 hertz. That means you have 11.11 milliseconds to render a lot of pixels. It is a low persistence display, which means the panel's on for a very short period of time. We'll talk more about that in a minute. And it's a global display, so the entire display is turned on and off at the same time. We don't have a rolling shutter. There's no complexity with that. It's a global display. It's really, really nice to write to. The frame buffer is 2160 by 1200. It's a stereo frame buffer. So each eye is 1080 by 1200, okay? In the back buffer. That's what you're sending down to the panels, okay? But you're going to render to an off-screen render target slightly larger than that. You're going to render about 1.4x in each dimension larger. So if you scale 1080 by 1200 by 1.4, you get 1512 by 1680, okay? That's 2.5 million shaded pixels per eye. That's over 5 million pixels per frame at 90 hertz. And that's the brute force approach. We're going to talk about how to reduce that number a little later. The FOV is about 110 degrees. We have 360-degree room scale tracking, meaning you have a large track space you can walk around in, which is important, which I'll talk a little bit more about in a second. And we also have multiple track controllers. So the developer edition, we're saying, is going to ship with 2 single-handed controllers that are fully tracked in the same absolute space as your HMD is, which is pretty awesome. So just to give you a visual for room scale tracking, and this is one of the reasons why I love working at Valve. I asked the artist, I said, hey, can someone make me an image of like a generic human in a room scale tracked environment? And Tristan Reedford and Cam Fielden gave me this, which is awesome. And I love the dishes in the sink. So, but the idea, it's a pretty accurate representation of what we mean by room scale, right? Sort of a good-sized area that you can walk around in and you're fully tracked in. Your HMD's tracked, your controllers are tracked, and it's all in the same coordinate space. But this is important because we have this sort of mental model of VR right now where locomotion is sort of you WASD around, or you have a controller that you're moving your avatar through an environment. We generally don't think of it in those terms, and it actually matters to rendering because if you think about a room scale environment where you can walk up to things and walk across the room and inspect things up close, you have this interesting thing where the things in your tracked environment matter more for quality than the things that are outside of your tracked volume, right? So anyway, we'll talk more about this. I want to get that in your head because this is a lot of what I'm going to talk about is going to be based on the idea of having this tracked space that you're going to be in and you can inspect things up close. Okay, let's talk about that 1.4x scaler. So your back buffer is a certain resolution, and then we're going to render off-screen a higher resolution. So this is sort of VR 101. Let's just make sure we're all on the same page. The reason why we're going to do this is because the lenses in front of the panels, the optics, have spatial and chromatic distortion. So if you were to just look at this is a stereo render straight from the rasterizer. We haven't done anything to it yet. If we were to put this on the panels in the HMD, what you're going to see is a severe pincushion effect, and you're going to see chromatic distortion where you're going to see red, green, and blue separate slightly. So what we do is we're going to warp into the back buffer, okay, and we're going to do the opposite distortion that the optics have. So the optics do a pincushion, we're going to do a barrel distortion, right? The RGB shift in one direction, we're going to shift them in the opposite direction. So this counteracts the lens characteristics, the lens distortion to give you a nice image. So the smaller image goes into the back buffer. I have them separated just so they're aligned. And the thing I want to point out here is I tend to think about this as a shrink wrap, not so much as a barrel distortion. Because if you look at the pixels in the center of the screen, sort of an area in the center, there's a 1-to-1 pixel-to-pixel ratio for the pixels in the center of your screen. And the pixels on the outside, there's a lot of pixels that get squeezed in. And there's a lot of wasteful rendering that we do in VR. I'll talk more about how to optimize that later. But the whole talk is going to be based on a 1.4x scaler. That is a recommended scaler. You could actually you could scale down to say 1.2 or up higher, depending on the GPU you're on, if you have to buy yourself some perf back. So there's, anyway, the 1.4x is what I'm going to base the whole talk on. I tend to think about renderers right now in VR as shaded visible pixels per second instead of frame rate raw, because for VR it's a little more complicated. You're rendering stereo images that are larger than your back buffer, times your refresh rate. So I tend to think of it in these terms. So if you think about 720p at 30 hertz, last gen consoles, you have to shade about 27 million pixels a second. If you look at sort of the current gold standard of 1080p 60 hertz on a console, that's 124 million pixels a second you have to shade. On the PC space, the gold standard, if you can hit 30-inch monitor, native res, 60 hertz, you have to shade 245 million pixels a second. 4K monitors are new. If we look at a 4K monitor at 30 hertz, a little bit more, about 265 million pixels a second. VR, on the other hand, since we're rendering stereo with a 1.4x scaler, right, for two eyes at 90 hertz, you have to hit 457 million pixels a second, which is a lot of pixels, okay? We're going to reduce that number to 378 million pixels per second later in this talk. But that is a big number, and it's something to sort of that worries me, right? When you start looking at your renderer and you figure out, can my renderer actually hit VR as it's currently written? One way you can figure this out is if you have a non-VR renderer, just as a simple test, run it native resolution on a 30-inch monitor, turn out VSync. If you can hit 100 hertz, your renderer is at least performant enough to hit VR resolution. This is nothing about whether you're going to have aliasing problems, but you can at least performantly hit frame rate. All right, I'm going to show you a really quick 30-second clip from the Aperture VR demo that we're showing at GDC. If you don't get a chance to see it, if you're in Seattle, come stop by our office, and we're happy to show you VR demos. We've had over 1,000 visitors from the development community and other places that we've given VR demos to just in the last year alone. We give a lot of VR demos nonstop, so we're happy to show you stuff. We're going to put this on Steam for free. Oh, right. It's a spoiler alert. So if you don't like spoilers, you should close your eyes for the next 30 seconds. I've cherry-picked parts of the demo to not really spoil much for you. The big spoiler's not in there. There's also no audio on purpose because the writers did an amazing job with this. So there's no way I could have had any audio that wouldn't have ruined something for you. So it's visual only. It's a graphics talk anyway. So, okay, so here goes. I'll talk over it. Here's me with a track controller. I'm doing a video capture from my HMD. And I'm using the track controller, opening the door, and there's our old friend, and he's sitting there, and he's going to come on in. I couldn't show certain shots I wanted to show, but we're pushing a lot of geometry. I'm just cut forward in the demo here. All these moving parts here, because you're in this tracked space with this guy, you can walk up to all these moving parts. His moving parts alone are like 600,000 triangles or more. I forget the exact number, but there's a lot of triangles in there because you can get incredibly close to this guy, to all these parts, and see the shape and the detail in this model. Here's some brushed metal, some anisotropic lighting. He's sort of all over the place on him. You can see my track controller rotating stuff. But anyway, it's a super fun demo. There's a super high fidelity. We're pushing a lot of geometry, and we've done a lot to anti-aliase that scene. Doesn't do it justice, of course, on a 1080p projector, but you get the idea. So, all right, so let's talk about stereo rendering. So single GPU stereo rendering, I'll just hit the high points. I'm not going to spend a lot of time on this. I could give an hour-long talk on just stereo rendering, but I'm just going to get through this because I have way more interesting things to discuss. The brute force thing you can do, obviously, is run your entire engine twice. Run it for your left eye, all your gameplay code, all your scene traversal, generate your draw calls, do the whole thing again for the right eye. Don't do this. It's bad for all the obvious reasons. I don't need to explain that. You can use a geometry shader, which is also bad. When I first thought about joining the VR team at Valve about a year and a half ago, the first thing I thought was like, great, we can finally use the geometry shader for something useful, right? Nope, don't use it. It's really bad. So, let me compare it to the next thing, which is resubmitting command lists, right? So in D3D11, what we do is we build up our entire, our left eye's worth of command lists. And when we go to render, we update our global constant buffer that has all of our transforms in it with our left eye transforms, and we submit all those command buffers. Then we go back and update that that constant buffer again with all your right eye transforms and resubmit all those command buffers again. Okay? This is what we're currently doing. It's twice the API calls as using the geometry shader, but the geometry shader is never faster. Best case scenario, geometry shader is the same performance that we've seen in a bunch of our test scenes, but overall, we've seen the geometry shader be slower more times than not. So it's not a win, unfortunately, so far. But it might be later as we start to mess around with foveated rendering. If you're going to amplify more than two triangles, it might end up being a win, but we haven't gone too deep in down that road yet. So we're currently resubmitting command buffers. The thing we think is going to be better, which I have not implemented yet, that's why it's a question mark after better. Timothy Wilson gave a talk at the San Diego Virtual Reality Meetup, and he proposed this idea, which I think is super interesting, is you use instancing. And the idea is that if you have an instance count of 2, the odd instance is for the left half of the screen, even as for the right half. And you use the clip output of your vertex shader to clip against the left or right half of that back buffer, right? And you use a different transform as well. This seems like the right way to do it. It's half the API calls, and because you're rendering each model, left eye, right after each other, you're going to have improved cache coherency across the board in your vertex buffer, index buffer reads, and your texture reads. So this, to me, seems like the right solution. I've not implemented it yet, but I'm planning to the next couple weeks. But I just wanted to mention it. Google the name of that talk. His slides are super interesting. That's single GPU. Multi-GPU, on the other hand, multi-GPU is super important, right? AMD and NVIDIA both have different extensions they're working on, and they're both super interesting in different ways. But we've implemented AMD so far, practically doubled our frame rate. We've not used NVIDIA's yet, purely because of time. I got their extension a couple weeks ago. I haven't had time to use it yet, but I assume it's going to do great things as well. You're going to want to support this in your engine. And you can have the argument internally, how many customers are going to have multi-GPUs. Ignore that argument. The real reason why you want to support this is because internal, when you're developing a game, you all know this, you're going to blow past perf as you're developing. That's just how it is, okay? Normally, you get lower frame rate, not a big deal. In VR, you go low frame rate, everyone on your team feels the pain of low frame rate in VR. They put the HMD on and they go, please fix that. That's really bad. So what we're planning to do is everyone working on VR in our team is going to have multi-GPU solutions in their dev kits, and I'm just going to lie to everyone about the frame rate because, but you'll be able to blow past a single GPU perf and not drop frames and still hold solid at 90 hertz, and that's super critical. So you should implement these extensions whether you think your customers have them or not. Okay, that's stereo rendering. Let's get into the meat of the talk. So this first section is about timing, okay? It's about scheduling work. So let's talk about prediction first, okay? Prediction is your tracking system knows exactly where your HMD is and your track controllers are at any given point. But when you go to render, by the time the user sees the frame you're going to render, it's in the future. by a little bit. So we have to predict our poses forward, and your HMD driver will do this for you, but it's up to you to ask for how much prediction you want, how far out to predict those poses. And it's critical that you understand this, and you have a clear mental model of how this works. So the HTC Vive has low persistent global displays, meaning it's low persistent in that of the 11.1 millisecond frame, the panels are only lit for about 2 milliseconds, give or take, okay? So let's look at 2 frames sandwiched by 3 V-Syncs, okay? Here's the GPU, and I want to make sure, yeah, okay, good. So make sure there's no overscan on this, it'd be terrible. All right, so here's the GPU in green, and it's rendering a frame, okay? At the end of the frame, it's presented, right? And we tend to think about that, sometimes wrongly, that, oh, it's presented, now the user sees the image. Not true. What happens is the image gets sent down over HDMI, whatever your video connection is, down to the panels. It goes through the series of tubes, and it lands on the panels. And then, much later, we blast those panels on for 2 milliseconds, okay? So if you're predicting your pose, in this example, right at the top of your frame, if you're going to predict your poses forward, update that constant buffer, and render, you need to predict forward 2 frames. Because while that frame you just predicted is going to be presented on the next VSync 1 frame later, the customer doesn't see it. The photons don't hit their eyes until another frame later. We call that rendering to photons, okay? It's when you start to render to when the photons hit their eyes. And there's really 2 segments. It's render to VSync, VSync to photons. And you have to have a really clear mental model of this to think about prediction correctly. All right, keep that in the back of your mind. Let's talk about pipelined architectures quickly. So pipelined architecture is when you're rendering the current frame and you're simulating the next on multiple threads. I hope everyone here knows what that means. So let's look at 3 frames followed through the graphics pipeline. This yellow is your main thread, we'll call it, which is your game simulation rendering prep. What I mean by rendering prep is you're going to build up at least for our engine, we build up all of our command lists that we're going to submit to D3D on the next frame. And on the next frame, in blue here, that's our render thread on the CPU. We're going to go and submit all of those command lists that we built up on the previous frame, okay? And after we start submitting, shortly after that, the GPU, so below that black line is the GPU doing work. Shortly after you start submitting to D3D, GPU gets busy rendering that work. And like we talked about, VSync hits, image gets sent down over the wire, hits the panels, and we flash the panels on later. So if you're predicting your poses for game simulation, at the top of game simulation, you'd have to predict forward 33 milliseconds, okay? Now, how far is safe prediction and how far is good prediction where your tracking still good is really dependent 100% on that particular tracking system. The way we tend to think about it is just keep your prediction as short as possible, okay? So if you predicted 33 milliseconds, we like to repredict right before we start submitting to the GPU. And so we only predict 2 frames forward. And we have rock solid tracking at 2 frames. We don't need to predict later than that. That works great for our tracking system. But one thing to keep in mind is we are simulating with a different set of transforms than we're rendering with, okay? So we generally tend to conservatively cull on the CPU by about 5 degrees in each direction out of our frustum, because in that one frame, when we started to simulate to when we started to render, the user can be moving their head. And we've measured about 5 degrees is enough to cover that movement. And if you have managed to move faster than that, you're moving so fast you're not even going to notice an object popping in at your periphery. So 5 degrees is pretty safe for us. We think that's a good number. So, but the interesting thing is, the important thing is, you really want to get that GPU going right after VSync on its frame, which is why we think pipeline architectures are just critical for VR. You want to have that frame ready to go, all your command lists ready to submit by the time you're on the other side of VSync, and that's why you want to simulate one frame, submit the next. Super critical for VR. This all relies on knowing when VSync happens, though, right? In this example, we're basically waiting for VSync to hit, and then we're predicting our poses and submitting to the API, okay? So here's the simplest VR implementation that we know of that we basically can predict right after VSync. The way you get your render thread on the other side of VSync, so this is a trick that Ottman Binstock came up with about 2 years ago at Valve, and it's still the tried and true. This is the method we use whenever we're doing anything new. We call it the read pixel trick. You call present, you clear the back buffer, and then you read a pixel out of the back buffer, okay? This is a great trick to just fully synchronize yourself with the GPU and then predict your poses forward. It's a great way to get going. Another way to do it is, instead of reading a pixel, you can spin on a query, right? You can present, clear the back buffer, inject a query, and spin on it. And it's great for initial implementation. We keep this in the engine because it's a great thing to just go back to just to vet latency latency issues because it's a rock solid way to do it. But don't do this in a shipping product. It's really bad. GPUs are really not designed for this. If you don't know why, I suggest you watch John McDonald's talk from last year, read his slides about detecting the CPU-GPU sync points. Right? Anytime the CPU is waiting on the GPU to finish work, you're hurting yourself pretty badly. Let's take a look at why. You're going to get GPU bubbles. Okay? So here's a capture from NVIDIA Insight. These are your two vSyncs. I've drawn vertical lines for where vSyncs are. The 51 this is frame 51 of my capture. Hopefully everyone here has used NVIDIA Insight, I would hope. But here's 51, here's frame 51, and you'll notice that after vSync, there's about a 1.5 to 2 millisecond bubble where the GPU is doing nothing. Okay, you have 11.1 milliseconds to render a ton of pixels, and the GPU is doing nothing. You just threw away 15% of your perf because you synchronized with the GPU. So all those little blue bars stacked vertically are jobs on the GPU actively working. What you want that picture to look like is this. Okay, right after vSync hits, you want the GPU off and working right away. Okay, that's gonna buy you back 15% of your perf if you can manage to get the GPU to do this. Okay, let's talk about how to do that. So here's this algorithm called running start I was working on, started about maybe 6 months ago. And the idea is that, well, let's take another look at this image one more time with a little more detail. Okay, so you can see the gray bars up top. That's where we start. So vSync hits. We predict our poses forward, and you can see those gray bars are where I'm submitting all the work to D3D, okay? It takes about 1.5 to 2 milliseconds for the GPU to actually get busy working on that. Because you have to go through D3D, it's got to go down the driver's got to convert it to GPU instructions, and then that work has to get scheduled, right? And so it's about 1.5 to 2 milliseconds, which is more than reasonable if you really understand what's going on in that pipeline. It's nothing to be angry about. So we want to work around that. So the idea of running start is you give the drivers, you give the runtime a little bit of a running start. So 2 to 3 milliseconds before vSync, we think is a good window. You start submitting your work to D3D then. So you predict your poses forward from then, which means you're going to predict an extra 2 milliseconds. You submit all your work to D3D starting about 2-3 milliseconds before vSync. So when vSync hits, you're actually ready to start saturating the GPU. Okay? So like I said, keep in mind you have to add a little bit of time. In this example, where it's a 2 millisecond running start, you're going to predict 24.22 milliseconds to when the photons hit the user's eyes, which is totally fine. At least for our tracking system, it's rock solid. We don't have a need to have to repredict later. It's always good to repredict. There's nothing bad about that, right? The less prediction you're doing, the better. But for us, we've seen it pretty rock solid at 24 milliseconds total. And if you see the Aperture demo, you're getting a 24 millisecond prediction every frame. This all relies, though, on knowing when vSync happened, right? Because you have to start your work before vSync. Read a pixel trick is not going to help you because you can't spin and wait for vSync to hit. You've got to start before vSync happens. So the question is, how do you know how far you are from the next vSync? The answer is pretty bad. It's tricky. You really don't know. Like rendering APIs don't give you this data. There's no API call. It's like how long since the last vSync or how long to the next vSync. You don't have that data. So SteamVR and OpenVR, we've implemented an API that actually spins on, in a separate process, spins on wait for vBlank and marks the time and increments a frame counter. Okay? And then we expose that data back to the app by calling get time since last vSync, which now gives us enough data on the PC and Windows to actually schedule our work relative to vSync and be able to predict accurately. We also have the ability for HMDs that support it. If the HMD can tell the driver when vSync actually hit with a timestamp, then we can give you even more accurate data. Instead of spinning on DXGI output wait for vBlank, we can get that data straight from the HMD. But either way, the API looks the same, super useful. If you're not using SteamVR or OpenVR, you can do the same thing. Spin up a separate process, spin on wait for vBlank, and mark times and increment a frame counter, and you can get the same data. What we really want is GPU vendors, HMD devices, and rendering APIs really to provide this, right? We're kind of being a little sneaky. We're trying to get around the fact that there's no obvious call to get this data. But anyway, that's how we're doing it. But we have that data, so let's apply it. Let's get a running start going, okay? So here's the details. The idea is we have to keep in mind dealing with bad frames, which we'll get back to later. But the idea of a running start is you're going to inject a query right after you clear the back buffer. You're going to submit your entire frame. Then you're going to spin on that query before you call present. Okay, that puts you on the right side of vSync. It's really hard to describe with words, so let's look at it visually. Let's follow a few frames through the pipeline. Here's frame 1. Okay, we're 2 milliseconds before vSync. Forget how we got there. You'll understand on the next vSync, but just give me that. Pretend we got there. Predict your poses forward 24.2 milliseconds into the future when the user is going to see this frame, and then you're going to submit your entire frame to the GPU, okay, or to D3D, I should say. This particular example, it only takes about 1.5 milliseconds to submit the whole frame, and then the GPU workload is going to be pretty thick. It's going to be 11 milliseconds solid, so it's sort of the best and worst case, but it's a good example to explain running start. So back on the CPU, so above the black line is CPU, below the black line is the GPU. So back to the CPU thread, our render thread. We're going to spin and wait until after vsync. Forget about how we do that. We'll explain that in a minute. And then you're going to call present, and this is super critical. You want to call present on the same frame that the GPU is actually churning away and rendering that frame, okay? Because right after that, what you're going to do is you're going to clear the back buffer. So frame 1 is blue, frame 2 is going to be orange. On frame 2, you're going to clear the back buffer, inject an event query, and then you're going to spin on that render thread and calls to time until next vsync, and you're going to wait until you're at your running start 2 milliseconds before vsync. And then you're going to predict your poses forward 24.2 milliseconds. And then when you're done submitting, you're going to spin on the query you injected after you cleared your back buffer, okay? Now, this isn't a CPU-GPU sync point because you're not flushing the GPU. You're waiting for an event query to pass, but you've already submitted your entire frame's worth of rendering after it. So what that actually ends up doing is if you look on the GPU at the bottom, the first thing that happens in the frame is the back buffer gets cleared and that event query finishes. So what that spinning on that query does is it puts you on the right side of vsync and puts you on the frame that you're going to render on the GPU. After that, frame 3 is green. You're going to clear the back buffer, inject a query, spin and wait until running start. And you're going to do the same thing all over again. Predict forward 24.2 milliseconds, submit your whole frame, and then spin on the query you injected after that clear. Okay? This is the running start algorithm. This is how you implement it. It might be a lot to digest, but the thing you might be thinking about is, why do I need to spin on that query, right? Like, we already have this call. I'm already spinning. When I'm waiting to running start, I'm spinning on the call to time since last vsync. Why can't I just keep doing that and spin until after vsync? The problem is if you drop a frame, okay? And let's look at a bad frame. So in the same picture, let's take that first frame, the blue frame, actually takes longer than your 11.1 millisecond budget. It might not even be your fault. Windows might just decide to index your hard drive for no good reason, okay? You have a web page up in the background. Something's going to happen. You're going to miss frames. It just happens. You will drop a frame occasionally to no fault of your own. And what happens is, if you're just spinning on the CPU until the next vsync, you're going to become latent from that point forward, and you're always going to be predicting a frame behind, and as you move your head, the whole world's going to swim a frame behind. It's really bad. So spinning on the query, what that does is it forces you to resynchronize after a bad frame so that you're rock solid predicting after that, okay? So in this example, that spin on the query is going to actually spin for an entire frame because that query that you injected way back there on the left won't actually pass until the GPU starts rendering that frame, right? Because the first thing that's going to happen all the way on the right is it's going to clear the back buffer, and that query finishes, and that's when your render thread gets released and starts doing its work. So that's why the query is critical. Anyway, that's running start in a nutshell. Hopefully that made sense. This is a solid 1.5 to 2 millisecond GPU perf gain. It will buy you. For us, it literally bought us 15% perf across the board. Our engine was just 15% faster because you got rid of that bubble at the top of the frame. Super critical. If you're using NVIDIA Insight, you want it to look like this. You want to see you're submitting a couple milliseconds before vsync. Right after vsync, that GPU should be busy doing work. Okay? Another useful tool is Microsoft's GPU view. And the yellow bars at the top is the GPU doing work. This is a much heavier workload. I did a different capture here. But right after vsync, you can see the GPU at the top there busy chewing through workloads. And you can see before vsync, about 2 milliseconds is when we're submitting to the API. Okay? This is what you want to see. And if you're not using these two tools, if you're doing VR rendering, you're not using Insight and GPU view, you should. You should really start using these tools. They're so critical. You really want to saturate the GPU. You have 11.1 milliseconds to render a lot of pixels. Okay, let's get into the next topic, which is aliasing. Okay? Aliasing is I've spent a little more than a year full-time on VR rendering at Valve, and I've spent easily half my time, more than half my time, trying to work on aliasing problems. Aliasing is pretty bad. Aliasing is absolutely your enemy in VR. It will burn so much of your time. Hopefully this will save you some time. The reason it's so bad is the camera, which is your head, never stops moving, right? You can say stand still and you can try, but your head's always moving a little bit, right? You're a meat puppet. You can't hold still. You're just always moving a little bit. So anything that aliases, you have jaggies that are going to crawl. If you're just standing still, any aliasing will just crawl nonstop. You can't stop it. It's pretty bad. So you have to spend a lot of time on anti-aliasing the hell out of everything you're rendering. However, the disconnect is that we're rendering a lot more pixels than we normally render. You'd think that, that we would have less aliasing problems. Well, it turns out because we have such a wide field of view, each pixel actually covers a larger angle than anything we've really done before. So let me give you an example. This is a number straight out of Michael Abrash's blog post when he was at Valve a couple years ago. It's a super clean way to think about it. If you're sitting in front of a 30-inch monitor at arm's length, your monitor is about a 50-degree field of view, okay? So at native resolution, you're getting about 50 pixels per degree on average. It's not linear, but on average, you're getting about 50 pixels per degree on that 30-inch monitor. If you're on that same monitor, but you're only running at 720p, okay, you're getting about 25 pixels per degree. That's, again, 50-degree field of view to a full-screen 30-inch monitor. In VR, with a 110-degree field of view with a 1.4x render target scaler, you're getting only 15.3 pixels per degree. I had to add the 0.3 to feel good about myself. But you get 15.3 pixels per degree. It's pretty low res compared to anything else we've rendered. And so it really makes you take a step back and figure out and realize we have to increase the quality of our pixels in addition to having to render a ton more of them. So we have to make a few different sets of trade-offs that we would otherwise not make in our renderers, I think. So first things first, let's talk about edge anti-aliasing. We think 4x multisampling is sort of the minimum quality bar. Okay? You don't necessarily need multisampling, but you need any algorithm you're going to do really wants 4x multisampling minimum. Okay? Forward renderers win in this case, so you can just turn that on trivially, and it works in forward renderers nicely. The Source 2 VR renderer that I showed, the Aperture demo, that's a forward renderer. And we've made very specific choices and trade-offs about the renderer. I can talk more about that later, but maybe in the Q&A session. But MSAA is so critical. We use 8x MSAA whenever we have the perf to spend on it. We're 8x across the board, and it looks amazing. It looks so good when you have 8x MSAA. It's really worth it. But if you are a deferred renderer, and we all understand the problems with MSAA and deferred renderers, if you're trying to use an image space anti-aliasing algorithm, the thing I urge you to do is get your engine to toggle on and off MSAA and that image space algorithm, even if you just need to hack together a forward renderer to do so. You want to stand in VR with an HMD on in a tracked environment and toggle it on and off and look at the sparkling differences when you're standing still, because that is a really good way to vet that your image space anti-aliasing algorithm is good enough, is going to hold up to whatever else is going to be shipping. Okay? But look at 4x and 8x, because 8x is going to be sort of the beginning gold standard for what anti-aliasing looks like in VR. Don't forget about jitter supersampling, right? You can use the sample modifier on your interpolator struct, and you can actually get the GPU to do jitter supersampling. So don't forget about that. That's a great upgrade for customers who have multi-GPUs or GPUs that get released later. Okay, let's talk about normal maps for a moment. So I've heard a lot of people in the industry, online and blog posts, on social media, giving talks at different conferences or gatherings, saying normal maps are dead in VR, they're not good. I couldn't really disagree more. Mostly. I mean, I mostly disagree, but there are cases where people are right when you're saying normal maps don't work, but they actually work great in a lot of the cases, and we use them all the time. So let's talk about what doesn't work first. So what doesn't work is feature detail that's more than a couple centimeters big, or even a centimeter big. If it's in your tracked volume and you can walk right up to it and inspect it, you can't fake shape, right? We're humans, we have two eyes. In VR, you have stereo vision. You can walk up to something up close and you can see the geometric shape. I don't care what the lighting says, what the normal maps say, you can see shape. So if you do something like this, here's just one example. I grabbed this randomly from something an artist was working on, but you can see it's sort of a curved shape, and it's got screw heads in it and some other feature detail. In VR, if you can walk up to this thing, this looks really bad, because you're looking at it going, it's a flat quad. I can see it's a flat quad. It's right there. Which is funny, because a couple of years ago, if an artist were to model screw heads, you go to them and go, can you please stop modeling the screw heads? You can't, no one's going to know. Just put that in a normal map, please. Now the artists do that, and we go to them and go, can you please model those screw heads? It's like, it looks really bad. We need to see the geometry. I can see that it's flat, right? So the artists are getting the opposite answer from us, which they love. But we have to be very careful about this, right? We're pushing a lot of geometry. The aperture scene, by the way, I think at max we're pushing 12 million triangles total per frame, which includes a Z prepass, our shadow rendering, and our color buffer. We're pushing a lot of geometry in a renderer. And we try not to get that high, but you end up pushing a lot of geometry because you have a lot of high fidelity content. But So let's talk about what does work, that we know that doesn't work. But what does work is you can actually apply that same trick to things that aren't in your tracked volume. Right? Think about that picture of the room scale tracking. When you're making experiences where you're not moving the avatar through an environment, where the things you can walk up to are the things you can physically walk up to in that space, you now have this quality bar, this metric where things in your tracked volume have to hold up to inspection up close. You have track controllers. You can pick something up and look at it. You don't even have to get awkwardly close to something. You can just bring it to your face and look at it. So things in your track volume, you can't do this thing with, but things outside your track volume, you can absolutely bake normal maps. We do it all the time, and it works phenomenally well. Right? One of our artists, Steve Cody, kind of taught me that, where we had these amazing staircases that are sort of just outside your tracked volume, which is all modeled, and then there's another track, the same staircase that's far away. And I go, I'm like, can we maybe do something that's not so high poly? And he goes, that's 2 triangles. What? I go, okay, I look at it and I'm like, oh, okay, you're baking that down to a quad. You carded a staircase, and in VR, you believe that it's correct because your eyes at a certain distance start buying into lighting cues, not so much into the stereo viewing of it, right? So these tricks still work great. All the things we've been doing with normal maps for years still work. The things that work in your tracked volume, things that you can get up close, are what I call sort of surface texture and fine details. This still works great. You can still get away with a lot of this, and we use it all the time. But normal maps have this problem, this fundamental problem that we're all very familiar with. Okay, so let's look at the normal map mipping problem. Okay, here's a Blindfang specular, pretty simple sphere with a normal map on it. If I were to super sample this, pull the camera back, do 36 samples per pixel, it looks like this, right? As this sphere minifies, as it goes far away from us, it should look like this, and that's the correct answer, okay? What we get right now, though, in most of our renderers is we push that sphere back, and with just MIP normal maps, it looks like this. It looks like this glossy mess. It's like someone sprayed cooking oil all over your object, right? And artists go nuts over this because they art past something up close, it looks amazing, and then it minifies, and it just becomes this glossy, disgusting-looking thing. So there's a lot of research that's been done in this area. I'm not going to do a full literature survey here, but the first thing I saw that tried to solve this that was usable for real time was the guys at ILM working on, I think, one of the Hulk movies about 9 years ago, did something called spec VAR maps, which was a super interesting thing to think about. I know Dan Baker did lean mapping. You've got Toxvig at NVIDIA did something as well. Like, there's a few different algorithms and solutions that are interesting, but none of them really solve the problem the way we wanted to solve it, and it kind of hit all the notes we were trying to hit. So let's talk about a solution that we put in place to solve this. So let's first talk about why we get that glossy mess. Any MIP filter that sort of generates an average normal is going to lose roughness information. Okay? So let's look at an 8x1 flat normal map. You have 8 normals, flat, pointing all up. As we MIP that down to a 1x1, you're going to get the perfect answer. It's going to be a flat normal, which is exactly what that 1x1 should look like for that flat normal. Congratulations, your math works great. Okay. Now let's look at a better example where you've got an 8x1 normal map, but there's roughness. Your normals are pointing all over the place, right? As we MIP that down to a 1x1, what you're going to get is exactly the same flat normal. These should absolutely not be the same. You've just lost all of that roughness information, okay? Which is why things become a glossy mess. As you minify it, our low MIPs of our normal maps are always representative of a perfectly flat, smooth, glossy surface, which is the wrong thing. We've lost all that information of our normal map. So here's a normal map visualization of a sort of a simple normal map. Here's metal siding, so you can see sort of vertical ridges. And if you look all the way on the right, the 1x1 MIP, what I'm rendering here is I just render a single point for every vector. I flatten my tangent normals into a -1 to 1 space, and I just render a dot for each normal and just kind of see where the distribution of normals are. And this is a good way to visualize it, I think. And if you look at a 2x2 MIP, if you look at your normal map and break that into quadrants, the upper left quadrant of your normal map, I plot all those points to the upper left quadrant of that visualization, lower left, so on, and a 4x4. Keep in mind that even at a 4x4, this is started at a 4K by 4K normal map. At a 4x4 MIP level, this is 16 flat normals. I mean, there's no data in here. When you MIP this down, you have a flat normal. You've lost all this information. And in here, what we have is anisotropic information. There's anisotropy in here. As you minify this, and if you're going to light this correctly as you minify it, you need to retain anisotropy in your lighting to actually capture the range of normals that contributed to each one of those texels in your normal MIP chain. Okay, let's use this as an example. So the idea was to encode this roughness information in every texel of every MIP of our normal map. Okay, and so here's one way to think about it: is we can basically store a single isotropic value, which I'm visualizing as a circle, is the way I think about it anyway. That's basically the standard deviation of all of your 2D tangent normals from the highest MIP that contributed to this texel. Meaning, if you take all the normals that contributed to this texel of this particular MIP, you take the distribution of all those normals, take the standard deviation of all those normals, and that's effectively a roughness value that you can use in your shader. Okay? So let's take a look at what that looks like. I'll get into how we do it. But on the left is just a simple box filter normal map. On the right is using this filtered, is by using this roughness information, the standard deviation that we retain through our whole pipeline and apply in our shader. And what happens is instead of it going to this glossy mess on the left, it actually retains the correct look that you want on the right. Now for VR, this is so critical, okay? I started working on this a couple years back at Valve. We haven't really used it because, I'll be honest with you, in a normal renderer, yes, it helps, but it doesn't even come close to how much you need this in VR. And the reason is the difference in scale you're going to view an object. In a regular game, the difference in scale is how far you're going to look at an object to when you get up close to it. And by close, you can get this close to something. In VR, you can get this close, and that difference is enormous in how high quality your normal maps are, the fidelity that you're rendering. When it minifies, everything becomes this glossy mess like is on the left. So it's so critical to get this right. Okay, so let's go back to this. So again, if you store the standard deviation, you get this isotropic value. It's basically just a roughness parameter. It's a single value you can store alongside each normal of each texel in your normal MIP chain. Okay. But if you look at this, you realize, because this distribution comes from that metal siding normal map that I just showed you, there's really anisotropy in here. So what you could do instead is store two values. You store the standard deviation in x and y separately, that I tend to think of as the dimensions of an ellipse in tangent space. Okay? And so when you start thinking through this, you realize that you can store an axis-aligned ellipse in tangent space, which can give you axis-aligned anisotropic lighting. And it's aligned with the axes of your tangent U and V vectors in world space. Okay? So this ellipse can either be wide or tall. It can't be rotated with this particular, with this method, right? So you have these two values. So the interesting thing about this is, before we go much deeper on that, let me just talk about what the artists also author is. The artists are going to author roughness anyway, but they tend to author it in terms of gloss, which is just the inverse of roughness, right? The artists like to author gloss maps because that's what they've authored for years. So dark is a matte surface, white is a really shiny surface. Roughness is just the inverse of that. So in our texture compiler, the first thing I do is I read their texture and just invert it. So everything works in roughness, but it's good for the artist to have a nice interface. What we do is, if you look at the image on the left, this is isotropic gloss. This is just standard roughness. It's a grayscale gloss value. But they can also author red and green channels independently, and they can actually author anisotropy along those two axes independently and control the strength of anisotropy in each of those two directions. Okay? What we do is we MIP their artist gloss map, we turn into roughness. So we MIP that roughness map, and at each MIP level, with the roughness information we're going to create in our MIP chain from our normal map, that is the standard deviation of those normals, we just simply add them together. At each MIP level, we sum all those parameters together. And effectively, you can think about one of those as being free. Either the artist gloss map is free, or the roughness information we generated in our normal map is free, because this is all at texture compile time. We're just adding these two together. So there's no overhead in doing this work other than you're spending some cycles when you're compiling your shaders to generate this extra information in your normal maps. All right, let's look at a representation. Let's look at what we can represent in our renderer. So the two axes here along the bottom is the tangent U roughness, right? So very rough values to the left of 1 is very matte surface. Very low roughness is very high gloss. And vertically is your tangent V roughness, okay? And when they're identical, when they're the same along this diagonal, you get just a nice isotropic highlight. Off axis, though, you're going to get anisotropy. And you're going to get this anisotropy that's going to be aligned with your tangent U and V vectors in world space. And because they're controlled independently, you have a lot of range. It's not like you only pedal the metal. You can only do brushed metal. No, you can actually do things in between. You can get subtle variations in your textures. The artist can author this per pixel, or per texel, I should say, on their model. So that example I showed you with green and red on the last slide, that's a model that has some anisotropy going horizontally, some going vertically in tangent space, right? So it gives them a lot of control over the look of those surface, and ultimately, you just need 2 additional values to store this 2D roughness information. We generally store our normals as 2D tangent normals anyway. So what I realized is if I can fit this extra data alongside an alpha green encoding of our normal map, shove that into the red and the blue channels, If it compresses well, which it turns out it does most of the time, the storage is free and the fetching is free. You get these two roughness parameters basically for free in your shader. 95% of the time, it's free because it compresses fine. Certain situations it doesn't compress as well. It has some bad artifacts with the normal compression. And so we'll let the artists opt out and put that into a separate texture or just uncompress it. But most of the time you can get away with a DXT5 compression and it holds up in VR. And it's so critical because that you have good specular. Because when you have good specular in VR, you can stereo fuse that reflection, right? If you have a light in a room shining off of a tabletop surface, with good specular, you can look at it and you can actually stereo fuse the distance to that light, and it looks amazing, okay? And so any compression artifacts in your specular, in your normal, you're going to read pretty well because you have stereo vision off that reflection. All right, so let me give you a visual representation of how we compute the specular lighting. So if you want an isotropic highlight like we have on the right, one way to do that is you can actually generate two anisotropic terms. In this example, they are the same specular exponent, effectively. And you can compute an anisotropy along tangent u and tangent v and multiply them together. And you're going to get this nice highlight. Okay, I'll show you the code to do this later. But if those exponents are different, though, so for example, if your tangent u has a very low exponent, but your tangent v has a very high exponent, your shape's going to be an anisotropic light shape. And this is fundamentally the concept of how you can get anisotropic lighting pretty efficiently in real-time rendering. And here's some shader code. I'm not going to step through the shader code, but so at the top is a function that takes our 2D roughness value and turns it into a diffuse and specular exponent and scale. The next chunk is isotropic diffuse lighting. So it's basically a Lambert term, but it's raised to an exponent. And that's because we want to represent a slightly wider range of BRDFs, you can think of it as, where really rough surfaces do want a slightly different diffuse term than really shiny, shiny smooth surfaces. So we have a little bit of an exponent that ranges between like 0.6 and 1.4 based on our roughness parameter. I did experiment with anisotropic diffuse, and it looks great in some cases, but it's really not worth the instructions, so we're not doing it. We have a lot of pixels to render. The anisotropic specular lighting in the middle, this is the code for that. I won't explain it in too much detail, but you can see there's two chunks of code, and at the bottom I'm multiplying them together. That's what I was showing you in the image visually. And at the bottom is isotropic specular highlight. So the artist can look at something and say, we're not getting anything from the anisotropy on this material, so let's opt out of that and just go to a cheaper blend fong with this modified scalar. And this 0.33 is really just to normalize the brightness. Now, where I'm at with this research is sort of when I work on something like this, I tend to do a bunch of rapid prototyping of just trying to feel out what I want the algorithm to be. And I was trying to think through roughness and anisotropic roughness. So you do a bunch of prototypes and you come up with something that you think is good, and you put a system in place just to get the artist to tune with it. That's sort of where we're at now, right? I've got this system, this code, that works, that does what we want visually. There's not a whole lot of science behind it, I'm not going to lie, but we're at the point where I'm at the point where I would then do the next phase, which is now let's figure out the real math. How would we make this something that would be publishable, right? And that's really where the real work happens. But I'm at the point now, I'm sharing this really early on, mostly because we think that anti-aliasing specular is so critical to good VR. We want to just give as much data as we can to other devs. But this is unfinished work for sure. I mean, you work through the math. It's interesting. It works. But I want to push this further. Ideally, I'd like to work with someone external that has the time and bandwidth to do something smarter with this core concept. But this is what we're using in all of our VR renderers. It works amazingly well. The artists have a lot of control over specular, over anisotropy. And what they author up close holds up as we minify it. And you know, that's great and all, but there's a bunch of stuff, but we don't have any normal maps on. So if you have a mesh with no normal map on it, everything I just told you is absolutely useless. Buys you nothing, because there's no normal maps to MIP, right? So you don't get that roughness information as things minify. So if you look at the robot and all of his parts, there's no normal maps on that particular model, because the geometry is so high res, you don't need normal maps. So what happens is, as that model minifies, you get the same problem where you get this glossy aliasing mess, and you're like, what? There's no normal maps. Why is that happening? Well, it's the same problem, but just to think of it a little differently, right? When you MIP your normal map, when you actually fetch from a lower MIP, you're representing that one normal you're using for lighting actually has a range of normals, a range of roughness that you lost with that one normal. Well, same thing with vertex normals, right? As your geometric normal gets interpolated, you get your pixel shader. We're using that single interpolated normal. But that normal actually represents a range of normals that pixel covers. If you were to project that pixel shape onto your mesh, there's a range of geometric normals that you're representing. Same problem, different solution though. So here's the solution, 4 lines of shader code. I'm using partial derivatives of the interpolated vertex normals to generate this, what I'm calling a geometric roughness term, okay? Here's a visualization of it on the right, and the idea is pretty simple. You take the ddx and ddy of your interpolated vertex normal, and that's going to give you the change in that normal across from that to its neighboring pixel. And for pixels that have the same normal to their neighbor, so that tabletop or the wall that's all black there, it's the same normal pixel to pixel, so there's no roughness information there. It's a flat normal. The normal you're using is the correct normal. However, for curved surfaces, depending on how close you are to it or how far you are from it, you're going to get a range of normals represented. So you can see anywhere where there's curvature on these models, you're going to have a higher geometric roughness factor. And these few lines of shader code do an amazing job of anti-aliasing all of your specular on your high-res meshes. And traditionally, this hasn't maybe been as big of a deal, but in VR, that little model there, I mean, these little models, that phone is like 30,000 triangles. It may sound ridiculous, but you can walk up to that phone and look at it, and it holds up and it looks amazing. Things just pop, and it adds to presence when you're in this space, in this tracked volume in VR. You can walk up to something, and it holds up. Its shape holds up to the fidelity you think it is. It works wonders. So anyway, again, this is somewhat of a little bit of a hack. You see there's a 3-3 exponent. That's really there. I fine-tuned that. That was really to match the roughness parameters, the standard deviation that feeds into the shader math that I just showed you. It matches the same look and the same scale. So it holds up alongside of the MIP normal maps and how the math is treating that. Again, I want to do deeper research in this and actually figure out what I think the right math is. But this math works and it holds up and we're super happy with it. And it's really efficient, right? That's another reason why I haven't gone much deeper is the shader code for both of these things is pretty efficient as is. And I'm afraid that if I do the real math, it's going to get more expensive. But we'll do the real math later. So that's aliasing. The last section is going to be a bunch of miscellaneous VR topics. This will go kind of fast, probably be less than 5 to 10 minutes, I think, of a few different topics that are super interesting. First thing, one more note on normal maps. We're really bad at storing normal maps. We all have been doing a pretty bad job of it. So what we generally do is we just take our tangent normal and we drop the third component and we flatten our normal that would basically land on a hemisphere when we flatten it down. And in the numeric range, we're only actually using about 78.5% of that numeric range. And we're not even making good use of that range because if you think about, if you were to plot a normal every degree off center, you have a lot of normals that are going to be centered, that are going to be tightly coupled towards the center of this image as you flatten a hemisphere of all your normals that you can represent. So, and we're not using the full range, we're not using it great. And like I said, in VR, you can stereo fuse specular, and you want that to look really good. So you want to get the best, resolution of normals. You want to make best use of that range, so you have good quality normals. So that's a bad representation. Instead, what we're doing is we're using a hemioctahedron encoding, which I got from this paper from Journal of Computer Graphics Techniques. Read this paper, super interesting. It was just published last year. And the idea is that you take all the normals that can be on the surface of a sphere, and you can map that onto an octahedron. You can unwrap that octahedron into a 0 to 1 texture space, and then we can take that center diamond, actually maps to the top half of the octahedron, which is exactly what we want, which maps to the top half of that sphere, and scale and bias that out, rotate and scale that out to fill the 0 to 1 range. This is a much better use of the range, of the numeric range of your normal map. And to decode this is only about 6 instructions, 5 or 6 instructions. So it's super cheap. We do it. That is now the standard that we use inside of Valve for VR normal maps. You also get a better distribution. The normals are better distributed, more evenly distributed over that hemioctahedron than it is on flattening a hemisphere. Super smart. It's a really great paper. Read the paper. It's literally 6 instructions. I think it's 5 maybe to decode it. It's super fast, worth every instruction. Okay, another topic, scale your render target resolution. Again, I keep talking about the 1.4 scaler, but That's a recommendation, and it's all about the optics. It's all about, when I was showing you the image shrink wrapping up and down, it's all about picking an area of texels in the middle of your image and keeping a 1-to-1 pixel-to-texel ratio, okay? You can go down to 1.2 if you need. Don't go down much farther than that, but you can. You know, if you need to buy PerfBack, that might be the best choice. It might be the best axis to scale on. But you can also scale up for faster GPUs. Anisotropic texture filtering, 3 seconds on this, use it. We have it forced on to 8x for all of our color and normal maps, okay? When you turn on, and you make it toggleable in your engine, if you're in VR and you toggle on anisotropic texture filtering of your color maps, the HMD, I swear, it looks like it's a higher resolution panels in front of you. Something about it, those texels being nice and crisp as they go into the distance buys you so much visually. Your brain buys into thinking that you're looking at a higher res panel. Absolutely do this. You can crank anisotropy up and crank that render target scaler down, and you can find this balance where it feels like it's the same res and much cheaper to render. Definitely play around with anisotropic texture filtering. We have it turned off for everything else, though. Everything else gets trilinear, that's it, because it makes no big difference visually. We have to keep our performance as high as possible. Noise. Noise is your friend in VR. You absolutely love noise. Noise should be added to every pixel. So gradients are horrible in VR, and we have good displays. They're not GIMP displays. It's an 8-bit 8-bit pixels, but as you're looking around in VR, because you're light locked out and you're fully tracked, your brain buys into you being there, gradients just pop. You can just see gradients worse than anything. Banding is horrible. So we add noise. We've been using this trick since Portal 2 on the Xbox 360. Yeston, one of the programmers at Valve back then, wrote this code, and we've been using it for years. It's a nice algorithm. It's like just a few instructions. This was performant on an Xbox 360. It's fine for VR. I tuned one of their values just to kind of work better in VR, but we do this on the way into the frame buffer for every pixel we're going to render. Every pixel gets dithered slightly. Few instructions, absolutely do this. Environment maps. So there's an online article down here, image-based lighting approaches and parallax-corrected cube maps. Please read that. It was written a couple years ago, and I really think it should be renamed to environment maps for VR because it's so critical, right? Environment maps in VR, your environment maps are at infinity. So if you're reflecting the skybox, it works great. Environment maps just work in VR. You look at it, and you can stereo fuse that that's really far away. But anytime you want to use environment mapping in an interior space or things up close, it breaks down. It hurts your brain to look at bad specular reflections because the environment map, you're looking at it, I know the ceiling's right there, there's a shiny surface, and your brain just goes, oh, no, because you can see the reflections. You're stereo fusing it at infinity, and it's wrong. So you need to use some kind of distance remapping of your environment maps. We support both sphere remapping and box remapping. Box is a little more expensive, but in the Aperture demo, all of our flat surfaces, we're using box remap cube maps, and it works phenomenally well, okay? We don't make them mirror surfaces, so you can't tell we're not updating them with dynamic objects, but there's enough visual information there where you can stereo fuse the reflections, and it makes sense, and it works, and it looks amazing. So please read this online article. If you're not up to speed on what I'm talking about, read that article. It's absolutely worth your time. Oh, this is a good one. Okay, so Stencil mesh. This is going to buy you another 15% perf boost in your engine, okay? So the idea is, we also call this the hidden area mesh in the Steam VR API, is you want to stencil out all the pixels you can't actually see on the panels, okay? There's a complex setup here. Your eyes are behind a set of lenses that are then going to project onto the panels. You can't actually see all the pixels on those panels. And so the idea is to figure out a screen space mesh you can render and stencil out all the pixels you can't actually see. All right. Alternatively, if you can't use the stencil buffer for some reason, because your renderer is already using it, you can also render it to near Z and early Z reject all those pixels. Okay. But the idea is that your lenses produce, at least in the HTC Vive, produce a radially symmetric distortion, which means effectively we're projecting a circular area onto the panels. Anything outside that circle, you're not going to be able to see. So let's take a look at that. So here's what our normal back buffer looks like that we would send to the frame buffer. And if we mask all the pixels that you can't actually see, the image actually looks like this, which looks like two circles, which actually matches the radial distortion of those lenses. And this is all very closely tied to your optics designs, how the optics are paired with the lenses, how they're aligned with the panels. But these are the pixels, the red pixels here, are the ones you can't actually see. And I've done this where you push the HMD as close into your face as possible until your eyeballs are almost touching the lenses, and you still can't see those pixels. You can just barely see them out of your periphery, but it's really not worth rendering them. It doesn't look like a lot of pixels here, but let's look at our off-screen render target, the thing we're actually rendering, okay? Here's our unmodified, raw, unwarped view. If I overlay the stencil mesh,
that circle that projects to that red area, these are all the pixels you're never going to see on the panels. Your customers will never see these pixels, so you should absolutely not render them. So you have this mesh that we can generate that you can, the first thing you do before you render is you render this into the stencil buffer, and then every pixel in your scene, you stencil reject against that value. And you will just buy yourself a 15% perf boost almost across the board. Because you're almost always pixel bound. Okay, so here's another one of that visualization. Here's your off-screen render targets. After we're done rendering, we've stenciled out all those pixels. That's why they're all black. And then this is how it maps to the smaller back buffer. Okay, and if you watch the blinking back and forth, any pixel you see in that higher res in your higher res render targets map to something the customer actually sees. So you are no longer wasting performance in rendering pixels that you'll never see. And this is huge. This buys you. This is literally 15% perf boost across the board. If you're using SteamVR or OpenVR API, we're just going to give you this mesh because it's different per HMD. Okay? It's all about those optics and those panels and how they're aligned. So you'll have a different mesh per HMD, and you'll get a different level of savings depending on the HMD as well. If you're not using one of these APIs, it's pretty straightforward how to compute this. I won't go into it. If you stare at it, if you're a graphics programmer, you'll figure this out in 10 minutes if you just stare at it long enough. It's literally, for this HMD, for the HTC Vive, it's a 17% fill rate reduction across the board. We are almost always pixel bound, so it's a huge win. Think back to one of the earlier slides I talked about. In VR, we have to render 457 million pixels a second. That's 2.5 million pixels per eye. After we apply this stencil mesh, that's how we get down to 378 million pixels a second, because you only actually have to shade now 2.1 million pixels per eye, or 4.2 million pixels total in your stereo render. This is a huge win, okay? And between this and the running start algorithm, that bought us 30% of our frame back, and it's a huge performance win. So do that. The one last thing I'll mention is the warp mesh. So we keep looking at the warp, how we warp from our off-screen render targets to the back buffer. Well, we render that with this mesh, and this mesh is, I think, 48 by 48 quads, if I'm not mistaken. And the density of this mesh is, again, it's tied to your optics, and we dial the mesh up and down until we can see no distortion as we rotate around. And a 48 by 48 mesh works great. Each vertex has 3 sets of UVs. About how we fetch from red, green, and blue separately. It's VR 101 stuff. But anyway, when you look at this, you're doing this every frame. You're rendering this mesh every frame. And we're rendering a bunch of pixels that are just black. So let's cull a bunch of those polygons. All those polygons I just removed have UVs that are outside the 0 to 1 range. But if you look past that, there's still triangles that are all black. And that's because they're fetching from the stenciled out area from the stencil mesh. So let's kill those pixels, or those triangles, and you get this mesh, okay? Which makes me crazy because I'm OCD and I want it to be nice and neat. Like, there you go, that's good. It's a lot nicer. And my coworkers make fun of me for doing this, but even shaving off those little corners, it was another 1.5% fill rate savings on your warp mesh. So my craziness helps sometimes. But this is overall, this is 15% of those pixels were culled by just doing this simple optimization. And again, you're doing this every frame. So you're paying the cost of this mesh, of this draw call every frame. Get every instruction back to your artists. This is absolutely worth it. So we covered stereo rendering. We talked about prediction, the running start algorithm that's going to save you 1.5 to 2 milliseconds a frame. We went into anisotropic lighting and aliasing problems and how we MIP our normal maps in, we hope, a much smarter way. The geometric specular aliasing using screen space partial derivatives, super important. And the stencil mesh that's going to save you 17% of your fill rate, easily a 15% perf boost for us, and how we optimize the warp mesh. The stencil mesh and running start, like I said, that'll buy you 30% of your frame back. If you just do those 2 things from this talk, if you take away just those 2 things, you just got yourself a huge perf boost. And these 4 things, if you're using the SteamVR or OpenVR API, we're going to pretty much solve this for you, so you didn't even need to understand it or pay attention. But we wanted to share this. The reason why we're sharing this, though, right? Because you could say, well, why are you sharing it if you're already solving it for everyone? Well, we really want to make VR happen. We sort of don't care so much initially where VR succeeds. We want every platform that's doing VR to do the best job they can and help make VR happen. We're super excited about VR. So if you're not on our platform using our APIs, if you're on a console, if you're somewhere else in the mobile space, you can apply all these techniques to that space as well, right? And we want to do everything we can to help make VR happen. Thanks for your time.